Okay, I I understand that there's an exam for you coming up today, right? So here's the first decision you need to make. If you are thinking about coming in here and then preparing for the exam later, you can go out. You don't have to be here because I will publish the video anyway, so you don't have to be here. But once you are here, I hope that you pay attention. Otherwise, you will be wasting your time. Okay? Clear? You have a decision. You have an option to just go out, study in the library, or you can stay here. But if you stay here, I want you to pay attention. So before I start, this is where we are. Today, I'm going to finish Chapter 7. So we'll be finishing Chapter 7 today. We are a bit behind. Also, later on, I will write mainly today on the board. So if you are sitting at the back row, you might want to move forward. Otherwise, you cannot see my handwriting. Today's it's going to be a very lengthy calculations and handwriting. All right, so I have posted the results of the third quiz, as well as the self-assessment record. So you have until next Wednesday, I believe, next Wednesday, to correct any you have until next Wednesday to correct any mistake that you see. And we have one more self-assessment, which will be due next week. I think I changed the schedule. The self-assessment form, that will be the last one on Chapter 7, which will be due on 5th of November next week. And that is it. I don't have any more requests. Also, I feel that the group presentation is not very effective, so I decided to drop that from this point on. But for those groups that have not made any presentations, please look at this. Please submit 2 problems that you selected from Chapter 6 to 10. Any 2 problems from Chapter 6 to 10. Write it well, type it, write it well, and send it to me. I will publicize your solutions at this website so that everybody can share. So that will be counted toward your participations. Okay, again, for the rest of the class, I will not ask any groups to come up to present, but each group needs to send me 2 problems clearly written so that I can publicize on the website for everybody to share. Is that clear? All right. With that, then let me go back to the board to finish up Chapter 7. All right. Chapter 7, don't forget, Chapter 7, we are talking about approximate solutions. Approximate solutions. So you will be expecting to see different answers even for the same problems. And most likely you won't be able to know the accuracy of the solutions that you have obtained. So that's the downside of this chapter. We don't know exactly how accurate the solutions that we have obtained. But based on the experience, it won't be like too far apart from your true solutions. By that, I mean that anything between like 20–30% is kind of acceptable. You know, like civil engineering design, we have a high safety factor. Usually, we throw in safety factor of 2, 2.5, 2.2. So your analysis results might be safeguarded by a safety factors of 2, 2.5. So which means that the discrepancy between the approximate solution and the actual solutions might be acceptable if they are like in the order of 30%. And don't forget that even though you are getting an exact solution or correct answer, our structural analysis is still subjected to assumptions. So you just have to look around, you know where the assumption is coming from. So like the beams columns, we assume it's a line, but in reality, it's not a line. It's coming in with some sort of dimensions. Connections, we assume it's very ideal. It's a pin connections or point connections, but in reality, it's not the case. So no matter how accurate your analysis is, it's going to be different from the actual behavior anyway. So you have to realize that. I'm hoping that through the experiments, through the lab test, you also can reflect, you can comprehend, understand the limitations of the analysis. So you always have that in mind when you do analysis. Okay. Let me remind you again, if you want to study, prepare for the exam, in the evening, please go out. If you want to sleep, please go out. You don't want to waste your time here. All right? So I don't want to call upon you. If you fall asleep, I suggest you to go out. So we are talking about two particular methods. One is portal methods. The other is cantilever methods. And they start from assuming inflation points. So last time we talked about this particular examples. That it so happens that just by using inflation point assumption is already sufficient to give you the answer. So let me just put down the solutions for you, and we start from there. So this is a simple portal frame, 1 bay, 1 story, horizontal force. So please be reminded, we treat horizontal force and vertical force differently. So horizontal force, we use inflation points. So we start putting inflation point in the midspan of each component. And for this particular example, we don't need any extra assumptions because this is a 3-degree indeterminate structure. So 3 inflation points will provide you with sufficient conditions already. So the results, last time I show you how you can get the results. The result is I'm going to split this loading into 2 equally at the base. So it's P/2 shear force, and axial force up. And then bending moment at the base. So equal bending moment, pH/4 and pH/4. OK, so that's the solution we can obtain after we assume the inflation point and everything comes out from equilibriums. So again, by the way, these are, let me remind you, approximate solutions. The true solutions might not be these values. Okay? That's what I mean. You will be expecting about 20–30% differences between the true solution and this solution. So the question is, how can I get the true solution? Then I say that you have to wait until chapter 10 and beyond to get those true solutions. Okay? But it's going to be more tedious. Now, let's try to take this and then expand to more complicated structure. So let's look at this one and then understand what is the extra conditions and what is the Portal methods. So this is a 2-bay, 1-story, assuming I have a P loading. No, I don't want to give you dimensions because this is only a conceptual. This is only conceptual explanations. What is Portal methods? So look at the structures, and then we identify that this is a 6-degree indeterminate structures. 6-degree indeterminacy. So you need 6 conditions. So let's count. I throw in inflation point at the midspan of each component. So that gives me 1, 2, 3, 4, 5. 5. So I'm missing one condition. I'm missing one condition. Right? So if I have 6, then that will become, the structure will then become determinate. So where do I come up with the 6? Now, if you follow this approach, say that, all right, look at, I have 2 bays. So if I can just imagine that this 2 bay can be analyzed separately, like this. So each bay take on equal load. So which means that this is P over 2, P over 2. So I assuming that this 2 bay, they take on equal resistance of horizontal force. So this sort of give me one extra conditions. So together with that assumptions, with this assumptions and the inflation point assumption, that will give me just enough conditions for me to analyze this further using equilibriums. So if that is the case, then following the previous analysis results, this load, horizontal force acting on single bay, 1 story, is going to split equally into the 2 columns. So, which means that this force is going to be split equally onto the 2 columns. So it's going to be P over 4 on each column. Same thing here. It's going to be P over 4 and P over 4. So this is this column, and this is also this column. This is called inner column, and these 2 are outer column. All right. So as a result, the Portal methods, if you follow this path, so this is called Portal methods. So the Portal methods assume that the inner column, inside column, take on 2 times of shear force, while the outer columns only take on 1 time of shear force. Okay? So if you follow that, that is called Portal methods. So it assumes that each bay of your frame structures take on equal horizontal force. And the consequence of that is the inner columns will have twice amount of shear force in compared to the outer columns. Okay, so that works for shorter building. Now for higher building, taller buildings, then this kind of assumption doesn't work too well. So people then develop another method called cantilever methods, which assume some sort of actual force distributions. So we'll discuss about that after we finish this Portal methods example. All right, so with that, then you will understand why Portal methods work. So for instance, if I have 3 bays, so if I have a 3-bay frame under horizontal force, so shear force here is 1 time, inner is 2 times shear force, outer is 1 time shear force. So basically, there will be 2 additional assumptions involved in producing these results. The assumption goes like this. You split into 3 bay. So each bay resists P1, P2, and P3 force. Together, they add up equal to P. So the Portal methods assume that P1 equal to P2 and P1 also equal to P3. So these are equally split. So here are the 2 conditions to ensure that the loads are equally split. So sort of this provide you with the additional conditions in addition to the inflation point assumptions. So you have 1, 2, 3, 4, 5, 6, 7. 7 inflation points plus 2 loading assumptions. So that gives you 9 assumptions. And this is 9 degrees of freedoms, 9 degrees of indeterminacies. So the condition is just right for you to get solutions. All right, so that's how you can look at it, why the Portal methods can give you solutions after you throw in the inflation points plus the shear force relationship. All right, so with that, then you can use the methods more comfortably. It works. Once you provide those assumptions, then it will work just using equilibriums. So I'm going to give you one example. All right, so let's go. It looks very scary, and it's going to be a little bit time-consuming for you to get the solutions. But imagine that this is exactly what people did in the old times using hand calculations. So I have 2-bay, 2-story frame under loading. 10 kilonewton and 20 kilonewtons. I should give you the dimensions. Okay, so pretty complicated. So you're asked to analyze this frame using Porter methods. And at the end, you need to plot the shear force diagrams and bending moment diagrams. And I will ask, most likely in the exam, ask you to plot the bending moment diagram at the tensile side. So by that, you will need to know the sort of deformation shapes of the structure. All right, so let's do it. First, introduce inflation points at the midspan of each component. All right. And then throw in the shear force distributions. So this is a shear force at the first level. So I call this S1. And this is 2 times. This is 1 time. And this is S2. This is 2 times, 1 time. OK. So with that, then the rest of the calculations can be done using equilibrium. Let's do it. Let's do the top floor. Usually it's coming from the top floor down. So let's take the top floor. So this is 10. So I'm cutting above the floor. Put on the inflation point. Midspan. And shear force is easy to calculate the shear force. 1 time, 2 time, 1 time, total 4 times to balance that. So each is 2.5. 2 times is 5. 1 time is 2.5. So horizontal force is in equilibrium. OK? Now, because I need to get the shear force and bending moment diagram, so I need to get into the components. So with that, let me draw a more detailed structure. So this is a corner. Here is a vertical component. Here's a horizontal component. Joint. Middle column. And the right-hand side. Corner. And the right column. So I break it down. I try to get all the detailed shear force and bending moments. Put on the force. Here is a 10 kilonewton force. Shear force I already found. 2.5. 5. 2.5. Put down the inflation point, midspan. OK? All right. So watch my flow carefully. Start from here. 2.5, move up, equilibriums. Action reactions, 2.5. Joint equilibriums, action reactions, 7.5. So far, so good. So you can move up like that. All right. Here's a hinge. So you come over to hinge and then take the moment equilibriums. Right? Come over here, take a moment equilibrium. The length is 6 meters, half of the height, 6 meters. So 6 times 2.5, that gives you 15. So this is 15. Okay? Same thing, 15. And action reactions, 15. Good? Joint equilibriums, if you have a moment of 15 there, you should have another moment of 15 to balance that. Action reactions, 15. Good? All right. Now come over here. This is a hinge. So you take a look at this part. Take moment with respect to that hinge. This 15 needs to be balanced. And the ways to balance is by a shear force. So that will be 15 divided by the half length. 15. So shear force is equal to 1. Action reactions. Joint equilibriums. Action reactions. Equilibriums. 1. Whew. Okay. You see that? Yes? I know you will say that. I will repeat again using, how about using this one? Huh? Let me use this one. Okay, let me try to work it out on this one again, show you. All right, watch carefully. 2.5 goes up, equilibriums, 2.5, action reactions, 2.5. This is action reaction. Joint equilibriums, so that gives me this 2.5 there, and then this is action reactions, so this is 2.5. All right? You come to the joint here, hinge here. You take moment equilibriums. The height is 6 meters. So moment equilibriums require you to have a moment here, which is 2.5 times 6, 15. And then you do it on the top part. So this is 2.5. You take a moment for that part. So that will be 15. And then action reactions, 15. Joint equilibriums, this 15 has to be balanced by this 15. And then action reactions, 15. All right? And then this 15, if you come to this inflation point, moment equilibriums require you to have this shear force, 15 divided by this length. So that length is 10. So this shear force will be 1.5. Action reactions, this is also 1.5. Joint equilibriums, 1.5. Action reactions, and then equilibriums, 1.5. All right, done. Should I do it another time? We have 3 columns. I can do it 3 times. It's more like a magic, isn't it? I can start from shear force and then come out with Okay, any questions? Hey, those people at this back row, the last row, can you see? There are plenty of seats in front. Why are you watching a computer? I'll keep bugging you. If you don't pay attention, I'll keep bugging you. As I say, you have an option. You can go out to the library. You don't have to stay here. I'll be bugging you anyway. All right. Good? Are we good? Now, let's try to resolve the mid part. Okay. Everything is about equilibrium, right? Nothing fancy. I just do equilibriums. So look at this component, equilibriums 1, action reactions 1. Moment equilibriums, action reactions 15. Axial force equilibriums, action reaction 7.5. Good. Come over to this. Equilibriums 1.5, action reactions 1.5. And moment equilibriums 15. Axial force, action reactions 2.5. All right, done. The only part is the lower part now. So look at the joint. Look at this joint. Moment. Look at the red color. There's a moment counterclockwise, moment counterclockwise. So you need to balance those by clockwise. 30. This axial force and that axial force, they needs to be balanced by this force. That is a shear force. So that's 5. So this is shear force 5, action reaction 5. That shear force balanced with that. So perfect. No problems. No contradiction. What else? Axial force. Now, axial force is this directions. So we take a look at that and this. So you need an axial force of 0.5, 0.5. Balance that. Equilibriums, 0.5. Finally, bending moments, 5 times 6, 30. Complete. Isn't that beautiful? It's structurally beautiful, right? Okay, any part that you don't quite follow or understand? So that's the top floor. The bottom floor. Very scary, huh? All right, it's not that bad. The bottom floor. So this is a lower floor. So I have 20. Yeah, if you have 3-story, then it will take you about 2 hours. If you have 100-story, that will take you a few weeks, assuming that you don't make mistake in the middle. Okay, lower floor, action reactions, action reactions, and action reactions. So this is 2.5, this is 15, and this is 1. This is coming from that, action reactions. And this is coming from there. So 0.5, and bending moments 30, shear force 5, (0.5), and this comes from there. Action reactions, bending moments. Oh, I'm sorry. The direction is wrong. Directions is wrong. All right. So this is 2.5. This is 15. And this is 1.5. Now we need something similar to this. So let's do it. You know, if you know what to do, this is very, very straightforward. If you know what to do, just need to be a bit careful. Put on the inflation point. Put on the loading. And bending moment. Okay, ready? Oh, there's an external force here. External force. So we start from the shear force. 1 time, 2 time, and 1 time. So shear force is here. One time, 2 time, 1 time. So the horizontal force, total horizontal force is 10 plus 20. So 30. 30 split into 1 time, 2 time, 1 time. So it will be equal to 7.5. 15 and 7.5. Okay, we start from there. 7.5, 15, 7.5. Or you can also look at it this way. There's a 10 and 20, and then you cut a free body diagram at the bottom of the column. 1 time, 2 time, 1 time. to compensate total of 30, so this will be 7.5, 15, 7.5. Good? Are we good? You want to do it for me? Yeah. You're OK. All right, so let's go. The height, half of 16 is 8. 7.5 times 8. 60. Oh, I should work out the shear force first. Equilibriums, action reactions. This is 7.5. So 22.5 minus 7.5, so there should be 15. Action reactions, 15. So I'm working on the blue first. Now work on the red. Here, moment equilibriums. There, moment equilibriums. Action reactions, 60. And then work at this joint, 60, 15. So 75 action reactions, 75. Come over to this point. 75 divided by half length of 30, so 15. 75, 15, so that would be 5. So you need a 5 shear force. And then this is action reactions of 5. So this is 5 and 1, so it must be 6 here. Action reactions there. All right, carry it downward. So I will have an actual force of 6. So that's done, the left-hand side. So you can work on this side first. 7.5 carry up, equilibrium, action, reactions. So blue, 7.5, 2.5 acting at this joint, so equilibriums, 5. So that's kind of done. Now the red, bending moment, 7.5 times 8. So again, it's a 60, 60. So 60, 15. So this way, 75. And then you go to this point, moment equilibriums. So you should have a shear force 10. So that's be 7.5. 7.5. 7.5, 1.5. So it should be 9. And here, 9. Oof. Can you see? I don't think you have 3-colored pen, do you? So there's no magic. You just have to do it yourself. You try to copy, it's more harder. You do it yourself, it's much easier. All right, so from here to here. 15, carry 15, 15. Actual shear force, 5 and 5. So this is 5. So then that will give you bending moments, 75. All right. here, horizontal force of 5, shear force of 7.5, and the bending moments of 75. All right, done. The rest is this one now. Usually you have a ways to verify whether you get the correct answer because everything should be consistent. Backward, front, front to back should be consistent. So that usually I leave that as my double check. So look at the actual force. 0.5, 7.5, that will be 8, and then this is 5, so it should have 3. Yep, correct. 3, 3. Okay. Direction is not right, sorry. Direction is not right. All right, now it's corrected. And look at the blue. 15, 5, and then this is 5. This cancel, so 15. So you have a 15 to balance. Action, reactions. So that balance with that. That's perfect. That's a double check, right? You get 15 on top, and then you get 15 at the bottom. So that's a double checking for you. Moment equilibriums. 30, 75, 75. So 150 minus 30, so that would be 120. So here is 120. And here is the 120. All right, that complete the analysis. All right, the finishing touch will be plotting shear force and bending moment diagrams. Okay, this is painful. Let's do the shear force diagrams. All right. So, shear force diagrams, I'm assuming the coordinate system. I'm assuming the coordinate system like that, like this, and like this. That's the coordinate system I adopt. So look at the top. So this is going to be defined as a positive. So positive, nothing in between. So positive, nothing in between. So that is 2.5. Now the top part. Let me get all the columns out first. And here is 7.5. 7.5 shear force. Mid part 15. Top 5. this 7.5. Top 2.5. That's columns and the beams. So this is a negative. So negative and another negative 1.5. This is negative 5. And finally, it's negative 7.5. All right, so that's done. This is a shear force distributions. All right. So next is the bending moment diagrams. So that's the most difficult part. So if I also ask you to plot at the tensile side, let me erase this. Okay, bending moments. Look at this. So obviously, this is the tensile side. And here is a tensile side. So 15, 15. So there's an inflation point in the middle. Look at this. This is tensile, and this is tensile 30, 30. Inflation point in the middle. And this one, tensile side 15. All right, that's tensile side moment distributions. Look at the top. So this is the tensile side. Here is a tensile side. So 15, 15. I'm writing a smaller and smaller font size. It's too complicated. So tensile side, 15, 15. Okay, that's the top. Next is the bottom. So again, tensile, tensile, tensile. All right, got it. So column there, 60, 60. And then 120. So 120, 60 again. Okay, that's column, and then I have beams. Beams will be 75, 75. Seven five, 75. Okay, done. This is the moment distributions plotted at the tensile sites. Okay. Please come forward to take photo if you like. Let me give you 3 minutes. If you have any questions or if you want to discuss with your friends. Any questions? Raise your hand. Are you shooting photos? Am I blocking you? You can come forward. It's not very clear. Eh? Post it? It's not very clear. You better take your own photo. You have a 小米. Yeah. Okay. Any questions for this? You don't know how to ask, right? But I did this without calculator, right? So I'm doing hand calculations. I'm quite nice. Okay. Hey, guys. Any parts of the calculations that you are not sure about? Or do you have any other questions about this photo method? Exam paper. Of course. Of course. Of course. You can use as many colors you want. Yeah. So for sure, you're going to see this in the exam, right? For sure. Yeah. What? Of course. I only give you that promise. So any further questions about this? I'm going to very quickly wrap up. We still have another method called cantilever methods. So let me just, I need to remind you again that these are approximate solutions. And as you can see that if I work this out using cantilever methods, the solution is going to be different. And the differences are not small. So please be reminded that this is the price that you have to pay. Basically, this is an indeterminate structure. So we are trying to analyze this using determinate means. So that's why you end up with a conclusion like this. And as I say that, I won't be surprised to see the difference ranging between 20, 30, even 40% between the two sets of solutions. OK, so that's polar methods. Next, I'm going to go very quickly on the cantilever methods. I'm going to have the same example, but using cantilever approach. All right, so same problems, but using cantilever approach. So what is a cantilever approach? They have the same assumption for inflations. So previously, the polar methods assume shear force following some sort of distributions. And the cantilever methods assuming axial force follow some sort of distributions. Right? So they follow some sort of distribution for axial force. So what is this distributions? So let's take the top floor out and then show you what is the assumption involved in the cantilever methods. So this is the top floor. It's too bad. I might test you on this. All right, so assuming that axial force follow some sort of distributions. What distribution? It's a linear relationship with respect to the centroid of the cross sections of the columns. So imagine that this is a column that has a cross section A. This is another column that have a cross section A as well, assuming that they have the same identical cross sections. In reality, it's not going to be identical most of the time. The inner column usually is bigger because people imagine that they need to take on more shear force. So the inner column usually is bigger. But just for the illustrations, now we say that the column cross sections are exactly identical. And we find the centroid of these three areas. Do you know how to find the centroid of the three areas? Oh, you have to go to static. Static, we have a centroid calculations. Remember that? So summations xi ai over summation ai will give you the average location. So that average location is referring to the centroid locations. So what happened is you set up a coordinate system here. This is called x. So this area is located at 30 meters. And this is located at 50 meters. So summation xi ai is 0 times a, 30 times a, 50 times a divided by 3a. So that gives you this number called 26.67. So it's telling you that you have a centroid at this particular locations, which is 26.67 meters away from the origins of x. So for cantilever methods, it assumes that the axial force is linearly distributed with respect to the centroids. So here's the centroid locations. And it assumes that the magnitude of the axial force follow a linear distributions. So this force and that force and that force is linear with respect to the centroid. So this is what I mean. So it's a linear distributions with respect to centroid, linear relationships. So this force, that force, and that force follow a linear distributions. So if I assume this is Q, this force is Q, because I know the geometry, I know the locations, so I know this is going to be 0.125 Q upward, and this is going to be 0.875 Q. So I'm just trying to explain this is the assumptions adopted by the cantilever methods. So instead of you saying that shear force follows some sort of distributions, it assumes that the axial force follow this linear distribution with respect to the centroid of the cross sections of the columns. So that's the tricky part. But it turns out that this method works better on tall buildings. So if you want to analyze like 100-story frames, then most likely you need to use this method, which is more accurate than the Portal methods. All right, so if you understand that, then this is what we can do. We can crack the structure from here. So let's cut it over there. Here is a 10 kilonewton force. So actual force follow these distributions. This is Q, 0.125 Q, 0.875 Q. Of course, there's an actual force. Well, there's a shear force, no bending moments. This is the hinge locations. This is the internal. This is the inflation points location, so there will be no bending moments, but there will be shear forces and actual force. What you can do is you come over here. You come over here or come over there, it doesn't matter. Just take a moment equilibriums. You come over here, take moment equilibriums, and you find out the only unknown is Q. Okay? Moment equilibriums, summation M. So that will give you the Q value. So remember that you have to do it at the inflation point where you don't have bending moment. So you cannot do it here because there will be bending moments. So you can only do it here, here, here. All right, so with that, then your solutions can start. So this then is 1.26. This is 0.16, 1.1. All right, so then we can start our solutions. Oh, we'll do it quick. So the calculations after you get the actual force is very similar to the Porter methods. Okay. You want to see the magic again? Let me show you just 1/3 of it, all right? So let's, I'll put down the inflation point. Right. Trust me, right? Follow the color. 1.26, 1.26, 1.26. 1.26, 1.26. You see? One number leads all the way there. So that's 1.26. Moment equilibriums. $18.9. Joint equilibriums, 18.9. Action reactions. Moment equilibriums. Action equilibriums. moment equilibriums. Isn't that nice? I'm missing something here. 3.15, 3.15. 3.15 balance with 10, so that is 6.85. So I run out of space. 6.85 there. So I start with one number. Look how I can get the rest. I start from one number. Here again for you. Follow the color. 1.1, 1.1, 1.1, and 1.1. Now follow the red. Moment equilibriums, action reactions, joint equilibriums, action reactions, shear force, all right, equilibriums, and moment equilibriums. All right, done. So you can fill in the gap now. Let me show you some numbers here. Okay, so you can fill in the gap. So I know this is complicated, but let me do this. Let me post the solutions to the website so that you can double check. How's that? All right, so you can then compare the solutions of these two approaches. Okay, that's the end. Good luck on your exam.